Hey everybody, this is the makeup video for class on February 8th. February 8th. I believe that's the right day. Yeah. Apologies for the lateness of it. I just ran into time over the weekend. So after you watch this video and you mark your attendance, do mark your attendance for February 8th. So this is Co-16B, February 8th, 2024. We're going to go over a few things here. I'm going to hit some highlights from the chapters, sections. That's a little off out of focus there. 1 second. From sections of 5.3, 5.4, and 5.5, I believe, and 5.6 as well. Yeah, not a whole lot in 5.3, but a few things to say. So 5.3 is exponential and logarithmic integrals. But what I really want to say about that is it's really just like, it's more examples of u substitution. So really, when you see an integral, your first kind of go-to place after maybe simplifying it, like is to see if you can just do a u substitution. So for example, if you're going to integrate, I don't know, 1 over x plus 3, you could do a u sub here. You let u equal x plus 3, du is going to be 1 times dx. You can totally rewrite this as the integral of 1 over u du, and then that's just the natural log of the absolute value of u plus c, which is the natural log of the absolute value of x plus 3. C. But like we kind of talked about before, for these logarithmic ones especially, you don't have to do the u sub if the denominator, if the numerator is a constant and the denominator is basically a linear function of x. So for example, for the integral of 3 over 2x plus 1, you could do the u sub. You could let u equal 2x plus 1. Your du would equal 2 dx. I don't have a 2 dx. I just have a dx. So I'm going to divide both sides by 2 and multiply both sides by 1/2. So I'm going to have 1/2 times du equal to dx. And then start rewriting this thing. I'm going to write this as 3 over u. I kind of broke my own rule there. I should have done the dx part first. Dx is going to become 1/2 times du. And then the 3 over 2x plus 1 becomes 3 over u. I personally would choose to write this, bringing the 3 over 2 out in front. Then you have a 1 over u du. We integrate. The integral of 1 over u is the natural log of the absolute value of u plus c. And finally, we throw it back to x's and get natural log of the absolute value of 2x plus 1. Let's see, times 3. What I want to point out is that whenever you're integrating like 1 over ax plus b like this, and we did a whole worksheet about this, this integral, you could have just said, oh yeah, I know it's going to be 3 times the natural log of that stuff in absolute value. And then if I was going to take the derivative of this, the derivative of this would be 3 times 1 over 2x plus 1 times 2 because of the chain rule. But I don't have the 2 up here, so I need to multiply this by 1/2 or divide by 2, whatever you want to say, so that when we do take the derivative of this, it ends up being the thing that we started taking the integral of. And the derivative of this would certainly be 3 times, the derivative of this is 1 over 2x plus 1 times 2 times 1/2, and then the 2 and the 1/2 multiply to 1. So just to kind of go in that vein for a couple more examples, if I was going, start trying to rotate around to let me move things a little bit here to get more comfortable. What I would say is that if you're trying to integrate something like, I don't know, the integral of 5 over 6x plus 2, we can straight away say it's going to be 5 times 1/6 times the natural log of the absolute value of 6x plus 2. Let's see. And yeah, you would write this as 5/6. So this is kind of showing a little more. In fact, let's check. Take the derivative of that. The derivative of 5/6 times the natural log of 6x plus 2 in absolute value. Let's see. Is 5/6. Constant multiples hang out. The derivative of the natural log of some stuff is going to be 1 over the stuff times the derivative of that stuff. And the derivative of 6x plus 2 is 6. 6 and 6, those cancel out, or 5/6 times 6 is just 5. So you're getting 5 times 1 over 6x plus 2, or if you prefer, 5 over 6x plus 2. As we should, because the derivative of the integral should get you back to the function you started with. Let's do one more example like this, and then we'll change up a little bit. Let's say we have the integral of, I don't know, 3 over 4 minus 7x. You should try it on your own for a second before I show you how to do it. But again, I'm really not going to do anything. I'm going to say, well, if you really like, I don't think you need to take this additional step, but you could write it as 3 times the integral of 1 over 4 minus 7x. I don't find that particularly necessary. But then it's going to be 3 times the natural log of the absolute value of 4 minus 7x. And we're going to divide by the coefficient of x, or we're going to multiply by 1 over the coefficient of x, so 1 over negative 7. If you want to make it look nice, sorry, the plus c should be after the parentheses there. I would write this as negative 3/7 times the natural log of the absolute value of 4 minus 7x plus c. Just like that. I'm going to do it more complicated though. For example, you might have something like the integral of 2 over 5x plus 1 to the third. And I have to stress here, the integral of this is not 2 times the natural log of the absolute value of 5x plus 1 cubed. The reason it's not is because if you take the derivative of this, the derivative of this is going to be 2 times 1 over 5x plus 1 cubed, but if you multiply by the derivative of 5x plus 1 cubed, and we don't have that in our integral here, so that's not the right way to go. This is actually an easier use of. Easier, maybe that's the right word here. It's a different use of. I'm going to write this as 2 times 5x plus 1 to the negative third. And again, we could let u equal 5x plus 1, but I'd rather just do this mini u substitution in my head and say, okay, I've got u to the negative third, the antiderivative of u to the negative third, and use the power rule, and u to the negative 2 divided by negative 2. So I'm going to get 2 times my u to the negative 2 divided by negative 2. But then I can see that that x is multiplied by 5. And then if I were to take the derivative of all of this, the chain will make me multiply by 5. So I know I need to divide by 5 to counteract that. So if you take the derivative of this, the derivative of some stuff to the negative second is going to be negative 2 times that stuff to the negative third times the derivative of the inside, which is 5, which will cancel the 1/5. So this is the right answer. I would probably choose to rewrite it. 2 over negative 2 does divide to negative 1. So I'd probably write this as negative 1 over 5 times 5x plus 1 squared plus c. Or if you prefer, negative 1/5 times 5x plus 1 to the negative second. You should check on your own. If you take the derivative of this, you do in fact get that. Let's see, I think I have one more example for this. No, not really. Okay. Let's go ahead and look at the other stuff in this, the other kind of thing that's in this section, which is e to the x. So, and I feel like maybe I feel like I've mentioned this before, just to kind of cover my bases, and I probably should have said this before we start off here. Just as a reminder, the antiderivative of 1 over x is the natural log of the absolute value of x. And similarly, well, not similarly, but somewhat relatedly, because we look at e to the x and the natural log of x is being related because of the functions. The integral of e to the x is e to the x. So if we're integrating something like e to the 6x, again, we could do a u sub. We could let u equal 6x. I don't think we really need to, though. Du is going to be 6 times dx. 1/6 du is going to equal dx. We could rewrite this as the integral of, let's dx at first. Dx becomes 1/6 du, and then e to the 6x is e to the u. Pull out the constant multiple if you like. And then the antiderivative of e to the u is e to the u, which is going to be 1/6 e to the 6x. Let's see, and you can see, if we take the derivative of this, the derivative of 1/6 e to the 6x plus c is going to be 1/6 times the derivative of e to the stuff is e to the stuff times the derivative of the stuff. Here we see is 0. And then the 1/6 times 6 is 1, so you just get e to the 6x, like you should, because we integrated, we got that, and we differentiated what we integrated, and we got back to where we started. Again, you don't need to do this part. I'm just showing you that if you take the derivative of your integral, you should get back to the function you started. But that can then kind of inform us and say, oh, well, if I do like the integral of e to the 4x plus 1, I don't really need to do the u sub here when the thing that is in the choice for u is a linear function of x, a line, a y equals mx plus b. I know that since I'm multiplying x by 4 here, the derivative would make me multiply by 4 because of the chain rule. So the antiderivative is going to have to divide by 4. So I'm going to get e to the 4x plus 1 divided by 4. I prefer to write times 1/4 though. You should check. If you take the derivative of this, do you end up getting what you started with? You certainly should. Let's look at some more examples here. Let's look at some harder examples. So yeah, that's all well and good. In fact, why don't you all on your own real quickly find the integral of e to the 8x? I'll give you a second. Well, you should pause the video. Do it. Great. Now you did it. And now the answer is e to the 8x times 1/8 plus c. That's not an 8, that's an x. 1/8. Sorry about that. 1/8 times e to the x. Not every u substitution is a mini u substitution like this. Let's look at some other examples. Let's say we have the integral of e to the 1 over x cubed over x to the 4th. So as I've said many, many times, the thing that we want to choose for u typically, or at least a good starting place, is letting u equal the thing that's stuck either inside a square root, or inside a sine function, or inside a cosine function, or any trig function, or inside a logarithm, which we haven't dealt with already yet, or inside of the exponent, or something that's being raised to a power. So here there are two potentially good choices. One would be x to the 4th. One would be 1 over x cubed. You might fool yourself into thinking x to the 4th is the right choice, because if you chose, I'm gonna write it down, but oh, this is the wrong choice. If we picked u equal to x to the 4th, our d would be the derivative, which is 4x cubed times dx. And you might try to lie to yourself and say, oh, look, I have x cubed times dx, and I have that here. I do not have x cubed times dx here. I have the 1 over x cubed is in the exponent there. It is definitely not being multiplied by dx. So that's not the way to go. The way to go is actually to let u equal to 1 over x cubed, or as I would prefer to write it, u equal to x to the negative 3rd. I prefer to write it like that so that I can more easily take the derivative. My du is going to be negative 3x to the negative 4th dx. Or more conveniently written, my du is negative 3 times 1 over x to the 4th times dx. And I exactly have a 1 over x to the 4th times dx here. I would probably divide both sides by negative 3, so I would say negative 1/3 du equals 1 over x to the 4th dx. Writing this out so it's a little bit easier to manage, let's write this as e to the 1 over x cubed times 1 over x to the 4th dx. So we can really see that we're going to replace this 1 over x to the 4th times dx. It's equal to negative 1/3 times du. And this e to the 1 over x cubed is going to be equal to e to the u. So now we can rewrite this. Let's just use the same color here. We can write this as the integral of e to the u times negative 1/3 du. I'm always going to be a fan of bringing any constant multiples out in front of the integral. It's just a pretty standard practice. You don't really, I will say, you don't really need to do it here. Like it's kind of if you're doing the integral and in the middle, you see like there's a constant you can bring out. You might do that, but here you say, yeah, I know the integral of e to the u is e to the u, and this constant multiple is going to hang out. But the reason it works is because we can do this and say, okay, yeah. Now be careful here. It's easy to forget that you're actually doing something from this step to the next step. So from here to here, you get negative 1/3 times the antiderivative of e to the u is e to the u. And then plus c. And then finally, replace the u with 1 over x cubed, so we get negative 1/3 times e to the 1 over x cubed plus c. And if you took the derivative of this, not that you have to, but if you did, you would get that. Let's do a couple more examples before we move on to the next section. So let's say the integral of e to the 3x over 2 plus e to the 3x dx. So I would choose u. Oh, it's not quite working. I was going to try and show something, but yeah. Let's choose u equal to 2 plus e to the 3x. It's stuck in the denominator. My du is the derivative of that times dx, so 0 plus e to the 3x times 3 dx. I'll do this one slightly differently. Personally, James would choose to say that 1/3 du is equal to e to the 3x times dx, because I have an e to the 3x times dx right there. But if you like, you can solve for dx and say du over all of this, so 3e to the 3x is equal to dx. And then you can kind of make this weird intermediate step here. So I keep trying to move things around here. You can make this weird intermediate step where you rewrite this with x's and u. So this is e to the 3x over 2 plus e to the 3x times du over 3 e to the 3x. And then the goal here is to make all the x's turn into u's. So we're going to start by saying that e to the 3x divided by e to the 3x cancels out, divides to 1. And then the remaining 2 plus e to the 3x is equal to u. So we end up with the integral of 1 over u times du over 3. I should have been smart there and brought the 1/3 out in front. So it's 1/3 integral of 1 over u du. We know that the integral of 1 over u is natural log of the absolute value of u. And then finally, replacing the u, we're going to get 1/3 natural log of the absolute value of 2 plus e to the 3x plus c. I would leave it like that, but I will point out some people would rewrite it as 1/3 natural log of parentheses 2 plus e to the 3x plus c. And the reason we can, although we don't have to, we can drop the absolute values there because e to the 3x plus 2 is always positive already. I'm taking the absolute value, but it doesn't change anything. Let's look at a few more examples. I feel like, yeah, okay, yeah, good. I was worried. I wasn't worried. I was just hoping I had this example set up. So this example, I know that someone over the weekend asked me about a homework problem similar to this and like how it was solved. So the integral of 1 over 2 plus e to the negative 3x. This problem, I will point out, is not equal to the natural log of the absolute value of 2 plus e to the negative 3x. And the answer really here is if you think something might work, if you think an answer might seem too simple or too easy to get there, you should check what happens when you take the derivative. And you have to remember to apply the chain rule. If you take the derivative of this, you'll see that the derivative of the natural log of some stuff, and I'm going to drop the absolute values because I can here. The derivative of all that is going to be, well, the derivative of natural log of some stuff is 1 over the stuff, but then we have to multiply by the derivative of the inside, which is 0 plus the derivative of e to the stuff, which is e to the stuff times the derivative of the stuff. And that, which I would rewrite as negative 3 e to the negative 3x over 2 plus e to the negative 3x, definitely doesn't equal 1 over 2 plus e to the negative 3x. We got some problems. So when you see a problem like this the first time, it's kind of like, what the heck do I do? There is kind of a trick. Yeah, there's kind of two approaches. So I'll show you, I guess, the way you would deal with this if you didn't know the trick, maybe. So one thing you can try, it's really the same either way. I'm just gonna show you kind of a long way of doing that. Is writing this as 1 over 2 plus 1 over e to the 3x. And then you're gonna get the common denominator in the denominator. So I'm going to rewrite this as the integral of 1 over, I'm going to multiply this 2 over 1 by e to the 3x over e to the 3x. So I'm going to have 2 e to the 3x over e to the 3x plus 1 over e to the 3x dx. And this is going to equal 1 over 2 e to the 3x plus 1 over e to the 3x. And then finally, 1 divided by all this is the same as 1 times the reciprocal. So this is going to be the same as the integral of e to the 3x divided by 2 e to the 3x plus 1. That is a long way of doing something that I've always seen the easier way. So the easier way is to say, take your integral. And something that we often try is multiplying the top and bottom by the e to the opposite sign of this. It achieves the same result. So I multiply the top by e to the 3x and the bottom by e to the 3x. Look what happens. I'm going to get e to the 3x on top, e to the 3x times 2, and finally, e to the 3x times e to the negative 3x. We add those powers together, and negative 3x plus 3x is 0, and e to the 0 is 1. Oh, look, those look the same. So either way you want to get from here to there is fine, and now we have to actually integrate it. So we're going to let u equal the denominator, 2e to the 3x plus 1, and then the derivative du, sorry, I shouldn't say du is equal to the derivative, which is 2e to the 3x times 3 times dx. I have an e to the 3x dx, so I'm going to rewrite this as, I'm going to divide both sides by 6. So 1/6 du is equal to e to the 3x dx. So then rewriting this is going to be equal to the e to the 3x dx is my 1/6 du divided by my denominator, which is now just u. Again, if you're like me, we like to bring that constant out in front. You can write 1 over u du, or you can just write du over u with enough practice to be like, oh yeah, the integral of du over u is just the natural log of the absolute value of u. So then this is going to be 1/6 natural log of the absolute value of 2e to the 3x plus 1 plus c. And again, I'll just mention here, you could, if you wanted to, drop the absolute values because the insides are always positive, but not necessary ever. You can always include these absolute values when they belong. Okay, let's move on to the next section. We did a couple examples last class talking about area and the fundamental theorem of calculus. Well, let's just review a little bit. So I think I'm gonna grab some questions from this book as well. So the fundamental theorem of calculus says, well, there's actually two parts, but we kind of just focus on the second part. The fundamental theorem of calculus, and let me actually, I want to write this down kind of as necessarily possible here for you all. Sure. And the FDC says that the integral from a to b of f of x dx, which we typically think of as like the net area under f of x between a and b. So for example, like you might be thinking of a picture like this, a, b, and this area here, that is what this definite integral is going to be equal to. And it's equal to, excuse me, the antiderivative of your function, which you write in the capital, evaluated between a and b, which we write as capital F of b minus capital F of a, where you can either say capital F is an antiderivative of little f, but the easier way to write that, the more mathy way to write that is the derivative of capital F is equal to little f. That's the same thing, right? If capital F is an antiderivative of little f, then the derivative of capital F should be little f. So then we can do all sorts of examples. Let me grab something from the textbook here because I don't have a whole lot on top of my head. But yeah, I mean, we can really just kind of integrate to our heart's content. So for example, someone could say like, what's the antiderivative from 2 to 5 of 4x squared plus 3x minus 7? And then you could do the thing. So I'm going to get 3 extra. I picked some nice numbers here. This will be a good exercise in not simplifying. I'm going to get 4x cubed over 3 plus 3x squared over 2 minus 7x from 2 to 5. Plug in the top limit first. So I'm going to get 4 times 5 cubed over 3 plus 3 times 5 squared over 2 minus 7 times 5 minus, then you plug in the bottom limit second. 4 times 2 cubed over 3 plus 3 times 2 squared over 2 minus 7 times 2. On the test, I'd probably stop right here. This problem is not, I mean, you can do one more step if you really wanted to. 105 cubes is 125. 125 times 4 is 500. 5 squared is 25 times 3 is 75. 5 times 7 is 35. And then we could distribute the minus sign here and get minus 4 times 8 is 32 thirds. 3 times 4 is 12 divided by 2 is 6. And 7 times 2 is 14. But I really don't see any value in going any further unless you're specifically asked to. If you had to simplify this further, you would combine these two terms first. So you'd be like, oh, 500 minus 32 is going to be 468 over 3. And then negative 35 minus 6 is negative 41. Plus 14 is negative 27. And then 75 over 2, I would write as 37.5. And this actually does happen to be divisible by 3. And the way you can tell that is because 4 plus 6 plus 8 is 10 plus 8, which is 18. 18 is divisible. If the numbers add up to a multiple of 3, the number is divisible by 3, which is kind of cool. So this is actually going to equal to 468 divided by 3 is going to be 156. 256, and then minus 27 plus 37.5 is going to be plus 10.5. So you can write this as 166.5. Or if you prefer, 333 over 2. Again, you should stop like here at the very latest, I think. Let's look at some more examples then. So fundamental theorem of calculus really is just kind of like if you're just given a straight up a straight up definite integral, you anti-differentiate and then you plug in. Let's look at a couple more examples of this before we get a little bit harder. Let's say we have let's say, sure, let's do this one. Let's say we have, sorry, I'm trying to pick up good ones here. Yeah, let's do the integral. We don't have to be too easy. From -1 to 1 of 2x minus 1 squared dx. And while you certainly could do a u sub here, u equals 2x minus 1, I don't think you really need to. I think you can just multiply this out. Is equal to the integral from -1 to 1. 2x minus 1 squared is going to be 4x squared minus 2x minus 2x is minus 4x plus 1. And then we do the thing. Yeah. Going to be, I will point out you can't do the thing where it's an even function. You say like, oh, it's going to be 2 times the integral from 0 to 1 because this is not an even function. That 4x right there makes it not an even function. So it's going to be, I didn't write the integral symbol anymore, so I'm doing the integral. It'll be 4x cubed over 3 minus 4x squared over 2 plus x -1 to 1. So we're going to get 4/3 minus 4 divided by 2 is 2. Also, I'm just plugging in 1 minus plug in -1. So -1 cubed is negative, so you're going to get a -4/3. You're going to get a 4 times +1 divided by 2 is still going to be a -2. And finally, a plus -1, so -1. Notably here, the -2 and the +2 are going to end up canceling out. So we're going to end up getting 4/3 plus 4/3 and 1 plus 1. That's going to be 8/3 plus 2. 8/3 plus 6/3 is 14/3. Okay, let's do some harder ones. Let's say we had something similar, but we had, say, the integral from 0 to 3 of x minus 2 to the 9th. Now it's a little bit too extreme to actually multiply that. We could do a u sub here and let u equal x minus 2, but since we're letting u equal a linear function of x, we can skip that, I think, and just say, oh, I've got u to the 9th. The integral of u to the 9th is u to the 10th divided by 10. So we really had x minus 2. If we take the derivative of this, or if you prefer 1/10 x minus 2 to the 10th, the derivative of this would be 1/10 times 10 times x minus 2 to the 9th, and then the derivative of the inside is just 1. So that's exactly that. We should be evaluating from 0 to 3. Oh, there was a reason I wanted to do this one as a u sub, which I kind of forgot. Oh well, we'll just do this one as the next one. So then we plug in the 3. 3 minus 2 is 1. Minus, we plug in the 0, and you get 1/10 times 0 minus 2, which is -2. And that's something. I mean, we can write it out. It's going to be 1/10 minus 1/10 times -2 to the 10th will be positive. And 2 to the 10th power is 1024. And if you played that stupid 2048 game, you would know that as well. 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2 to the 10th. So this is really 1/10 times 1 minus 1024. So -1023 over 10. We got a negative number. Is that okay? Yeah, it's okay. Let me show you what I mean. So let me grab Desmos real quick. And, you know, and there's probably a way to actually calculate area using Desmos. I've never played with it enough to actually know that. But if so if you look here for a second, if we graph the function x minus 2 to the 9th, I am curious now. There has to be a way to find area, I bet. That's an n, not a 9. So between 0 and 3, in fact, we can even. Here's a cool thing. Here's the thing that I think is neat. You can, if you type little braces here, and then say 0 is less than or equal to x is less than or equal to 3. It gives you just the portion of the graph between 0 and 3. And obviously the graph is really, really negatively large when x gets closer and closer to 0, because negative to the 9th power is like super giant, right? It's way, way, way down. But so it looks like clearly most of the area under that curve is below the x-axis, which means going to be is negative. I do kind of wish I knew how to find the area of that, but I don't. Let's see. I wonder what. Let's try this. This is like, oh wow, that's cool. That totally works. So the way I did that was I just typed int. Neat. 0, 3, and then if you do the function, I wonder if it'll look colored into this. Probably not. I don't know about it. But they do give us a number, right? Because we got a negative 1023 divided by 10. Oh, I know how, if you want to like make it look cool, you can say we want y to be between this function. Yeah. Less than or equal to that, bigger than or equal to 0. So there's so notably, right? That's the part that's above the x-axis. To get the part that's below, you have to switch it up and say that you go like, and then for the part between from 0 to 2, say okay, now we want our function x minus 2 to the 9th to be less than or equal to. To get the equal to part, you just literally type equals after you type the less than symbol. Y. Ooh, that's a lot of graph. Less than or equal to 0, and then we only want the portion from 0 to 3. You don't need to be able to do this, but it's kind of fun. So look, there's actually it's kind of, I think it's pretty useful to be honest. So from 0 to 2, there's the part where y is below the graph, so all that area is going to be counted as negative. And then from 2 to 3, there's the portion that's above the x-axis, all that's getting counted as positive. And so then you do this positive part minus this negative part, this positive part minus this part here to calculate the net area above the x-axis. The net area is negative because there's more area below than above. Cool. Anyway, back to our regularly scheduled notes here. Let's share this. It's just the visualizer. Garbage on the screen there. I did want to do a couple of examples of area between curves where you're having to do a U sub for real. And I'm throwing my papers on the floor here, but I think I'm going to get out of the way. So let's see for a second. Okay, so yeah, let's pick something like that. Sure. Sorry, I'm trying to like waffle between what I want here exactly. Let's do something like this. Let's say we want to find the integral from, I'll make it limits integration in a second. Let's say we have, excuse me. Yeah, sure, let's try that. Let's do 2x squared plus 1 cubed, 4x on top. Yeah, like that. Make it easy. And then we'll go from 0 to, let's say, it's not too heinous here. Let's say 0 to 2. Okay, so this integral does require a u set. It's pretty obvious what it is. We're going to let u equal 2x squared plus 1. Our du is nice and perfect. Derivative of 2x squared plus 1 is 4x. Slap on the dx. We've got that. There are two ways to go when it's a definite. I'll show you my preferred way first, and then we'll talk about the other example. So the preferred way, I think, is to change your limits of integration. I'll point out, this is the integral from x equals 0 to x equals 2 of 4x over 2x plus 1 cubed dx. I'm going to change things to the language of u, and that includes changing the limits of integration to be u values. So when I rewrite this integral, well, first of all, the 4x dx is my du. The 2x squared plus 1 is my u, so I have a u cubed on the bottom. And my new u limits of integration, well, I'll point out that if I use this, then x equals 0 is going to give me u equal to 2 times 0 squared plus 1. I'm just plugging in the value of x there. So I get u equal to 1. And that's, since x equals 0 is on the bottom, u equals 1 is on the bottom. Similarly, if x equals 2, then I'm going to get u equal to 2 times 2 squared plus 1, which is 4 times 2, 8 plus 1 is 9. So I would probably rewrite this integral as the integral from 1 to 9 of u to the negative third d. And then I'm going to actually do the integration. We get u to the negative 2 divided by negative 2. We don't need a plus c. If you had a plus c, it would just cancel out because you subtract them. From 1 to 9. I always say from the bottom to the top. That's the correct way to read this. And then to evaluate this, I'm going to actually make it a little bit nicer. I'm going to write this as negative 1 over 2u squared, bringing that u to the negative second down at the bottom and the negative up in front. 1 to 9. Now we plug in the top limit first. We get negative 1 over 2 times 9 squared minus negative 1 over 2 times 1 squared. Just to simplify this a tiny bit, we've got negative 1 over 9 squared is 81. 81 times 2 is 162. Minus minus is plus 1 half, or 1 half minus 162. And yeah, you could get a common, well, 1 half minus 162. We could get a common denominator, multiply this by 81 over 81. You get 81 over 162 minus 1 over 162 for a final answer of 80 over 162, which reduces to 40 over 81. But you could probably just leave it like this, to be perfectly frank. Okay, that's the way I would recommend doing it. You change from x to u, you change your limits of integration, and you don't change back, right? We stuck with u and we never change back to x's, and that's perfectly fine in the definite integral where you have limits of integration like this. Or you cannot do that. You can say, I don't like leaving it from u, although I don't know why you wouldn't back into it either way. And I'm going to do this integral without ever changing the limits of integration. So if you do it this way instead, I think you have to keep writing x equals 0 and x equals 2. And not just 0 and 2. Like if you write this, from 0 to 2 of du over u cubed, that's wrong. Because what you're saying is u equals 0 to u equals 2 of du over u cubed. But we know it's not u. We know those are x values. So we have to remind ourselves that we have to remind whoever's grading our work that we know that those should be x values. So then we're going to get, I'd probably write this one more time, x equals 0 to x equals 2, u to the negative 3 du. It still integrates the same way. Still get u to the negative second over negative 2 from x equals 0 to x equals 2. But then we do have to plug back in what u is equal to. Again, I would probably rewrite this first as negative 1 over 2u squared. X equals 0 to x equals 2, and then plug back in that u is equal to 2x squared plus 1. I've got negative 1 over 2 times 2x squared plus 1 squared. From now, I don't need to write the x's anymore because we know those are x values. And then finally, plugging in the 2, you get negative 1 over 2 times 2 squared plus 1 squared. A lot. So 2 times 2 squared is 2 times 4, so plus 1 is 9 squared, minus negative 1 over 2 times 0 plus 1 squared, just 1 squared. So we're doing the same thing, right? We still have a negative 1 over 2 times 9 squared minus a negative 1 over 2 times 1 squared. But to me, this feels like a less nice way of doing it. I'm going to pause the video real quickly here. Not pause the share. I always do that the wrong way. I'm going to pause the actual video. So as I was saying, I think that's the way you should approach a u substitution with a definite integral, is to change your limits of integration, but you can do it either way. Oh yeah, so a few more things. Again, this is for just like, if you're given a definite integral with limits of integration, this is how you should approach it. You should integrate the function and differentiate the function. And then plug in limits of integration, plug in the top limit first, subtract, plug in the bottom limit second. Sometimes though, you're asked to find the area under a curve or the area between curves. So for example, someone might give you, say, something like this interval from, I don't know, 1 to 7 of the absolute value of 3x. Let's go with minus, sure. Minus, yeah, minus, sorry, 15. And yes, you can break this up. It's not that I recommend doing it, but you could totally, if you wanted to, say, oh, I know that the absolute value of 3x minus 15, I'm just gonna set the insides equal to 0. 3x minus 15 equals 0. You get 3x equal to 15, x equal to 5. You know that 5 is where you change the insides from being positive to negative. So essentially, what I'm saying is the absolute value of 3x minus 15 is equal to just 3x minus 15 if x is bigger than 5, and it's equal to negative 3x minus 15 if x is less than 5. You can throw on the equal sign whatever you like. Right, because for example, if x is, like 2, 3 times 2 is 6, 6 minus 15 is negative 9, and then the negative 9 gives you a positive 9. Exactly what I should. So, but that's not the way you should really do this. You should not really break this up as the integral from 1 to 5 of negative 3x minus 15 plus the integral from 5 to 7 of 3x minus 15. And those work just fine. But it's really more work than you want to do. What you really want to do here is you want to draw a picture. So you can say, okay, well, this integral here is the area under the curve y equals 3x minus 15 absolute value, or y equals the absolute value of 3x minus 15. And I can draw that. It's your typical V shape. It will look something like this. Sorry, where it's hitting the x-axis when x equals 5. And we're trying to find the area under this thing from 1 to 7. And again, your picture does not have to be perfect. We're just trying to find this area. So great, that's a triangle. I know how to find the area of a triangle. If I plug in 1 to my absolute value function, 3 minus 15 is negative 12, absolute value of negative 12 is 12. So that's going to be 1 comma 12. Similarly over here, if I plug in 7, 7 times 3 is 21, 21 minus 15 is 6. That's 7 comma 6. So this triangle over here, which we'll call, say, it's A1, has a base of 5 minus 1 and a height of 12. So this integral here is going to equal 1/2 the base of this triangle times the height plus, same deal over here, 1/2 times the base of that triangle is 2 times the height is 6. That's going to be, let's see, 1/2 times 4 is 2, 2 times 12 is 24. By the way, this part of the integral would equal 24. And then 1/2 times 2 is 1, 1 times 6 is 6, so plus 6. So this area, this integral over here would have an area of 6, and then 20 plus 6 is 30. And that's it. That is almost always the way you should approach an absolute value interval, is to just draw it if you can, and then look at the area of triangles. Cool. The other thing I want to point out, sometimes you're asked to find the area between curves. And we did one of those in class on last Tuesday. Let me show you another one. So here's one that's kind of terrible. We're going to do the, well, let's actually do it. We'll get to that one in a second. Let me do one over here. Let's say, let me use examples. Sorry, I'm looking at these. Okay, sure. Yeah, those are fine, I guess. Yeah. So, sure. Let's say we want to find the area between, yeah, the functions, or I should, yeah, sorry, I'm like waffling here. Let's say between y equal to x cubed minus 2x and y equal to, is that gonna work out all right? Let's say y equal to 2x. Yeah, that's fine. Okay. So it helps to graph this if you can, but it's not absolutely required. Let me show you. We want to find where these functions intersect each other. And if we set these equal to each other, x cubed minus 2x equal to 2x. Bring that 2x over. So x cubed minus 4x equals 0. Factor again. We're getting 3 points of intersection. And then what we can see is that, so we're without graphing, but we know we're going to go from -2 to 0 to 2, pick a point between -2 and 0, like 1. And this is exactly a time where I'd switch gears and say, I'm going to call this f of x and call this g of x because it's convenient to. So I plug in something like -1, f of -1 is -1 cubed, which is just -1, minus 2 times -1. So -1 plus 2 is 1. Whereas g of -1 is 2 times -1, which is -2. So on this interval from -2 to 0, f is bigger. So on the interval from -2 to 0, the function f is bigger than the function g. On the other hand, on the interval from 0 to 2, if I plug in, say, 1, f of 1 is 1 minus 2, which is -1, and g of 1 is 2 times 1, which is 2. And here, you can see that g is larger than f. So what that means for us is that when we do the integral here, we can't just do the integral from -2 to 2. We have to do the integral from -2 to 0 of the larger minus the smaller, plus the interval from 0 to 2 of the larger minus the smaller. Graphically, here's what's going on. The function y equals 2x looks like this. And the function y equals x cubed minus 2x. Well, I should say these intersect right when y is 2, sorry, x is 2, and 2 times 2 is 4. Here, 8 minus 4. So they're intersecting like 1, 2, here-ish, here-ish. What we've really got kind of going on is something that looks like this. Where in the interval from, say, -2 to 0, the cubic function, which is f of x, is the larger function. So like from here to here, it's going to be f minus g. But then from 0 to 2, now g is larger function. So from here, we have to do g minus f. That's why you have to kind of break it. There's more than 2 points of intersection like this. So you calculate this as an one here. So we're going to have the integral from -2 to 0 of f minus g. So x cubed minus 2x minus 2x plus the integral from 0 to 2 of g minus f. The fun thing about subtracting things in the opposite order is you basically just get negatives. So this first one is going to be x cubed minus 2x is x cubed minus 4x dx. The second one is going to be the opposite. 2x minus x cubed minus a minus 2x is going to be 2x plus 2x. So 4x minus x cubed. They don't just cancel each other out, so we have to actually do them each. So then we're going to get x to the 4th over 4 minus 4x squared over 2, -2 to 0. I should just write that as 2x squared plus 4x squared over 2 is 2x squared minus x to the 4th over 4. All of that from 0 to 2. So then we plug in and we get, so here first, right? We have to plug in 0, you get 0 minus 0, minus, you plug in -2. -2 to the 4th is positive 16. And -2 squared is positive 4. Plus, plug in 2 here, 2 times 2 squared is 2 times 4. And then minus 2 to the 4th over 4 is 16. And then that's going to be minus 0. So let's see, we've got -4 minus minus is plus 16 over 2 is 8. Plus, now over here we have 2 times 4 minus 16 over 4. So this ends up being 8 plus 8, which is 16, minus 8, which is 8. A lot of 8s. Cool. And sometimes, though, your region is worse than that, and you actually kind of have to draw it out. So, for example, someone might say, find the area bounded by, or bounded, yeah, sure. Yeah, bounded on the right by y equals x squared. On the left by y equals 8x, and above by y equal to 16. You graph these things. Here's y equal to x squared. And now I need to be a little bit careful before I start graphing anything else. So let's see where these things intersect. So y equal to x squared and y equal to 8x, if I set those equal to each other, my factor, I get x squared minus 8x equal to 0. So x times x minus 8 equal to 0. So I'm going to get x equal to 0 and x equal to 8. If x equals 8, y is going to be 64. So that might be a little too high. And then for the y equals 16, y equals 16 and y equals 8x gives me x equals 2. In fact, let's draw the y equals 16 here. And then for x squared and y equals 16, so those equal to each other, x squared equals 16 gives me x equals plus or minus 4. So that point there is 4 comma 16. That point there is negative 4 comma 16. And then for y equals 8x, the question is it going to be over that line? Like, is it going to be that, or is it going to be like that? And we can see that when x is 2, y is going to be 16. So right here at 2, that's where the line is going to hit. So we're going to do that. And now if we read this carefully, we're asked to find the area bounded on the right by y equals x squared. So this is the right boundary. This is the left boundary. And this line here is the above boundary. So we want the region bounded above by this line. So we're looking at this region here. To be very careful with your reading. Right? If they had said we want the region that is above y equals 16, it would be this part up here. We want the region bounded above by y equals 16. Kind of annoying. Okay, the hard part here, gosh, my shoulder soreness over here. The issue with this problem is that if we're going to do this in kind of a normal way, or integrate with cycle x, we have to break it up into two intervals. So at x equals 2, we switch from y equals 8x being the top function to y equals 16 being the top function. So they always said the area integral would be the integral from 0 to 2 of the top function minus the bottom function, plus the integral from 2 to 4 of the top function, which is y equals 16, minus the bottom function, which is still y equals x squared. And that would be a totally fine way of doing it. Or, if your teachers are doing this, and again, sometimes they don't, you could integrate with respect to y instead. So instead of thinking about adding up a bunch of vertical rectangles, you have a small width of dx, a small change in x, and the height of that rectangle is the top function minus the bottom function. We can think of adding up a bunch of horizontal rectangles. Where the width of them is a small change in y. And the length of them, or the height of them, is the right minus the left instead of the top minus the bottom. To do right minus left, we have to change things to be in terms of y. So this y equals x squared would become x equal to plus or minus the square root of y, because it's on the right-hand side, x is positive, so it's the positive square root of y. Over here, this is where x is equal to the negative square root of y. That's correct. And then this function here, y equals 8x, would become x equals y divided by 8. So then it would be the area equal to the integral from a low of y equals 0 to y equals 16. And then we'd have the right function, which is the square root of y, minus the left function, which is y over 8. Or written in a way that's easier to integrate, y to the 1/2 minus 1/8 y. And generally, this would be preferred because it only requires us to do one integral instead of doing two different ones. So often people will have you switch things up like this if it makes sense too. I don't think we need to evaluate this right now, although just go kind of say this. And you got other things here. I feel like there's one other thing. Maybe not. What I would encourage all of you to do is to do both of these integrals, or I guess all three of them. Do this integral and do this integral and calculate the area. I'll do the second one because it's easier. So if we integrate this real quickly here, the integral of y to the 1/2 is y to the 3/2 divided by 3/2 times 2/3 minus 1/8 times y squared over 2. Numbers are not going to be nice. So if we plug in 16, we get 2/3 times, okay, I'm just going to do it. 16 to the 3/2 is the square root of 16 cubed. So that's 4 cubed, which is 64. Minus 1/8 times, okay, 16 squared, I'm gonna write that as 16 times 16 over 2. So that's 16 divided by 8 times 2 is going to be 16 divided by 16. So I end up with 2 times 64 over 3, which is 128 over 3, minus a 16. If I multiply 16 by 3 over 3, that's going to be 48 over 3. And subtracting, you get 80 over 3. I would encourage all of you to do this integral and see that you should get the same answer, assuming I'm not very smart. I don't think I have, but you know. Okay, it's 10:48. So that will be somewhere. So I think we will have to save. There's all my area between. Let's do one more example like this, and we'll talk about the midpoint rule, and we'll talk about volume on Tuesday. So there's a couple. So in chapter 5.5, there's some area between curves. Let's look at one more example here. Sure. Let's do something like the region bounded by, yeah, let's say, trying to pick an even things here, sure. Y equal to 1 over x, y equal to x cubed, x equal to 1/2. I feel like the ones they're giving here are a little too easy though, but we'll talk about that. Too easy for that. But they're giving you more information than they really need. So let's graph the stuff. So y equals 1 over x, it's like this. Y equals x cubed kind of does this deal. They're probably going to intersect at 1, 1, like x is 1, y is 1, so they're going to intersect like right there. So y equals x cubed kind of does this. And then we're going from x equals 1/2. So again, this is the 1 point, right? So x equals 1/2 is 1 over, I shouldn't say from x equals 1/2. It's really, we should draw the line x equal to 1/2. And it always feels silly to draw the line x equals 1 because really you don't need that. So if we're looking for the region that has all 4 of these graphs as boundaries, well, it's this region here, which feels a little bit funky because kind of it's weird that x equals 1 is really technically a boundary, but it is. So here to find the area, you do the integral from x equals 1/2 to x equals 1, left to right, of the top function minus the bottom function. And then we would just do it. So the integral of 1 over x is the natural log of the absolute value of x. The integral of x cubed is x to the 4th over 4. From 1/2 to 1. Plug in 1, you get natural log of 1. I dropped absolute value because absolute value of 1 is 1. Minus 1 to the 4th over 4. 1 to any power is 1. Minus the natural log of 1/2 minus 1/2 to the 4th. Again, I don't feel like there's a great need to simplify here. I will point out though that the natural log of 1 is 0. So we could rewrite this as -1/4 minus the natural log of 1/2 minus is plus 1/2 to the 4th is 1/16 divided by 4 is 1/64. And yeah, that's fine. Although I will point out, you might be concerned because it kind of looks like this answer might be negative. And the area should always be coming out as positive. Right, area between curves should be positive. We're talking about net area above the x-axis vacuum. The actual area between curves should be positive. Here's why this is not negative, or at least how you can simplify this. So normally I wouldn't simplify this one. So if we simplify here, I'm going to multiply this by 16 over 16. I'm going to get -16 over 64 plus 1 over 64 minus the natural log of 1/2. -16 plus 1 is -15. So -15 64ths But here's the deal. Natural log of 1/2 is actually a -1. Think about the natural log now. You could actually write natural log of 1/2 as the natural log of 1 minus the natural log of 2. And so if you have the negative, and then the natural log of 1 is 0. So the negative natural log of 1/2 is the positive natural log of 2. And natural log of 2 is about 0.7. That's a lot bigger than 15/64. So this answer is positive, even though if you write it this way, it might not appear that way. All right, so that's kind of sections 5.3, 5.4, and 5.5. In class on Tuesday, we'll talk about the midpoint briefly, and we'll talk about volumes more in depth. And I know you all have a midterm on Wednesday, so yeah, that's what we'll do on Tuesday. I will also try to post, I'll try to write a practice exam today and get it posted up, and we'll also post some certification now, so you all have extra practice material. But definitely, I know we're a little behind the ball. I apologize for that. But we'll definitely talk about volume tomorrow, and then you all will have to practice your butts off for your exam on Val. Who gives an exam on Valentine's Day? It just seems cool. Anyway, I will see you all tomorrow in class on Tuesday. Again, after you've watched this video, please fill out the attendance form. It'll be linked in the video and the Canvas. But make sure you fill out the attendance form date for February 8th, 2024. Thank you so much. Again, apologies for the video being a little bit late, and I will see you all in class on and this.